Hello students, welcome to EPG Pathshala. I am Dr. Sanjay Kumar Chamoli from the Department of Physics and Astrophysics, University of Delhi. Today we are going to talk on module Radiation Detector Part 3 under the paper Nuclear and Particle Physics. After completing this module, the students will be able to number 1. Understand interaction mechanism of electrons in material medium. They will be able to differentiate between interaction of heavy charged particles and electrons in matter, and also they will have knowledge of interaction of X-rays, gamma rays in the medium. Charged particle in matter, electrons. In this particular slide, we are going to study how the electrons on entering in the detector interact with the material, or basically how they are getting detected. Now we know that electrons are basically charged particles. For electrons, major energy loss in matter is via Coulombic interaction. So first of all, we need to understand that what are the interaction mechanism for electrons in the medium. Here, since electrons are charged particles, and through the discussions in the previous slides or previous modules, we have learned that the incoming radiation sees the matter of the detector in terms of its constituents. That is, it does not look at the matter in terms of its element like aluminum, magnesium, germanium, silicon, not like that. But it sees the matter in terms of its constituent, means in terms of nucleus and electrons, and interact with them. So, when the electrons enter in the medium, they interact with the nucleus and they interact with the electrons of the medium. So, here we can say that since electron is a charged particle, entering electron is a charged particle, electrons of the medium are also charged particle. In that case, they will interact via Coulombic interaction and lose their energy. So for electrons, major energy loss in matter is via Coulombic interaction. Now what happens is, since entering electron and the electron of the medium are identical in shape and size, so it's an interaction between two identical particles. In this case, due to the Coulombic interaction, the incoming electron suffers energy loss as well as strong deflection. And since the electron continuously interacting with the electrons of the medium, so we can say that in every interaction, the electron is suffering huge deflection. So there is the loss of energy, due to which there is a change in the speed of the electron in the medium, and also since at each interaction the electron is suffering huge deflection, so there is a change in its direction. So speed is changing, direction is changing, it means the velocity of the electron is changing. And since electron is a charged particle, its velocity is changing in the medium, it means it is in accelerated motion. We know that whenever a charged particle in acceleration passes through a medium, then it starts losing energy in the form of radiation, which is called Bromslang radiation. So since the electron in the medium is in accelerated motion, so it will also lose its energy in the form of radiation, that is Bromslang radiation. So in case of electron, there are two interaction mechanisms by which the electrons lose their energy. The major portion of the loss comes from the Coulombic interaction, whereas the other portion comes from radiation loss. So for electron, energy loss in matter is via collision loss, which we commonly call as Coulombic interaction with the electrons of matter, and radiation loss, which we are calling as Bromslang. So total loss of energy for electrons in the medium, which is also called the linear stopping power, is given by dE by dx is equal to dE by dx collision plus dE by dx radiation. Now, if we want to see how much is the contribution of the two losses for electron, then usually we find that dE by dx, ratio of dE by dx for radiation to the dE by dx of collision is around Ez by 700. It means the energy loss, the radiation energy loss depends on the energy of the incoming particle E and the Z of the material of the detector. Now E minus and or E plus are the only charged particles in which radiation loss contributes significantly to total energy loss. So it means electron and positron are the only charged particles. Others are alpha particle, alpha proton, heavy ions, fission fragments, etc. They are heavy charged particles. But electrons and positron, because they are very light charged particles, in these cases, the radiation loss contributes significantly to total energy loss. Emission probability is proportional to E square by me square c square whole to the power 2. This sentence basically we can see in the light that since the other charged particles like alpha particle, heavy charged particle like alpha charged particle, protons, heavy ions, fission fragments, etc., all these are charged particles. They also suffer deflection of the path, but the deflection is very small as compared to the deflection of path for electrons. That is why in those cases also, that is in case of heavy charged particles also, there is some loss of energy due to the radiation, that is Brahmaström loss is also there, but that Brahmaström loss is negligible as compared to the losses that we see in case of electrons. So electrons and positron are the only charged particles in which the Brahmaström energy loss, which is called radiation loss, contributes significantly to total energy loss. The major differences between electrons and heavy ions are electrons move with relativistic speed. So this is now we want to differentiate that how the charged particles are different than electrons. Now electrons are very small size particles. So for a given energy, the velocity of electrons is very high as compared to the heavy charged particle like proton or alpha particle. So we can say that the electrons move with relativistic speed. Second thing, electrons collide with identical particles. It's very important because when the electrons enter in the detector, they interact with the electrons of the material medium. Since they are both electrons, so we can say that indistinguishability concept will be there. We cannot distinguish which electron is suffering the deflection in which direction because they are identical particles. So in this case, electrons collide with, in case of electrons, they collide with identical particles. So large deflection in path is there. Due to light mass, there is a finite probability that some of the electrons may be backscattered. That is deflection at 180 degree and leave material. This is very important because electrons are very light mass particle. They collide with the electron of the medium. So since it is a collision between two identical particles of same mass, same size, so there is a fair amount of possibility that in that collision the entering electron may return back. That is, it may suffer deflection by an angle of 180 degree. So though suppose 100, we can say that suppose 100 electrons enter in the detector, it may happen that only 70 got entered and get counted or get interacted within the medium, whereas 30 suffered the backscattering. So they come out of the detector and they are not counted. So this is the situation this is the situation which is very much there in case of electron and positron, that there is a fair amount of backscattering. Charged particle in matter, electrons. The backscattered electrons have considerable effect on the designing of detectors for low energy electrons, more for low energy and thin jet. It means when the electrons enter in the detector, they see the identical electrons of the medium. So there happens there basically some backscattering of the entering electron take place, and this backscattering is more for low energy electrons and high jet of the detector material. The maximum allowable energy transfer becomes W max is equal to kinetic energy of the electron by 2. It means when the electron tries to enter in the detector and interact, then there is a chance, fair amount of chance, that that electron will be backscattered. So overall, if we see that how much energy of the incoming electron is transferred in the detector medium, then it becomes W max is equal to kinetic energy of the incoming electron by 2. That is 50%, at the most 50% of the energy is transferred to the detector. Corrections needed in Bethe-Blalock formula for E minus or E plus. So now, as we have seen in our previous study, that Bethe-Blalock formula basically gives the cross section of interaction, or rather the stopping power of incoming charged particles within the detector medium. So that formula we can still apply for electrons, but we need to modify the Bethe-Blalock formula in order to apply it for electron or positron detection. For electron, corrections needed due to the following reasons. What are these reasons? Number 1, due to small mass, electrons suffer huge deflection in collision, because as we have said that when the electrons enter in the detector, they see the identical electrons of the detector medium. So it's basically the interaction between two identical masses, electromagnetic interaction between two identical kind of particles. So due to the small mass, electrons suffer huge deflection in the collision. So in the collision, the incoming electrons basically suffer huge deflection. Second thing, since collision is between identical particles, so indistinguishable. So if we track the electron in a particular direction, then we cannot say that whether this electron is the incoming electron or the electron of the medium, because they are identical particle, so indistinguishable. Charged particle in matter, electrons. So we continue our discussion about the Bethe-Blalock formula in case of electrons. So Bethe-Blalock formula for electron or positron radiations can be written as dE by dx is equal to dE by dx c plus dE by dx r. What is dE by dx c? dE by dx c is basically the Coulombic interaction. So dE by dE by dx c is given by the equation minus dE by dx c is equal to 4 pi me c square n by beta square bracket e square by 4 pi epsilon 0 bracket whole square bracket log tau square tau plus 2 upon 2 into I upon me c square whole square plus f tau minus delta b beta gamma minus 2 c by z, where f tau is a function given by 1 minus beta square plus delta plus tau square by 8 minus 2 tau plus 1 log 2 upon tau plus 1 whole square for electrons, and f tau is equal to 2 log 2 minus beta square by 12 bracket 23 plus 14 upon tau plus 2 plus 10 by tau plus 2 whole square plus 4 by tau plus 2 whole cube for positron. So now it is clear from the discussion in this slide that Bethe-Blasch formula for electron and positron has two contributions. One contribution in the stopping power is from the Coulombic interaction between electron, and the second contribution is coming from the radiation losses that the electrons suffer in the medium. So, the Coulombic interaction basically can be calculated as we have calculated in case of other charged particles, heavy charged particles. So, the Coulombic interaction, we have formula for electrons and positron. The two expressions are different as we can see here. So, the electron energy loss due to the Coulombic interaction within the medium of the detector is different for electrons than positron. Charged particle in matter, electrons. In this slide, we are going to study that how the radiation energy loss happens in the electron inside the detector and how it can be calculated. So, the radiation energy loss dE by dx R is given by is equal to bracket E upon 4 pi epsilon 0 bracket close E square n z plus 1 into E upon 137 m0 square c to the power 4 bracket 4 log 2E upon m0 c square minus 4 by 3. So, radiation energy loss is given by this formula. Now, if we want to see that how is the path of the electron inside the matter, then the picture given below shows the path of the electron in matter, and we can see that the electron path is not a straight line path as in case of heavy charged particle, but electron's path is a zigzag path, and so the distance covered by the electron inside the detector is basically different for different electrons. On the right hand side, there is a picture where the stopping power of electrons is given as a function of energy for different elements, for different material medium of the detector. So, here you can see that the curve is given for lead, aluminum and air. So, now both kind of losses are being shown. The radiation energy loss as a function of energy increases with increase in energy of the electron or positron. But on the contrary, the collision loss means the energy loss due to the Coulombic interaction between the incoming electron and the electron of the medium. It basically decreases with increase in energy. So, here you can see that in the picture the collision energy loss is less in case of lead, but more in case of air, whereas the radiation energy loss more for lead, but less for air, and they both vary as a function of electron energy. Gamma ray, X-ray in matter. Now, in this slide basically we are going to study that how gamma rays or X-ray photons interact with matter. Gamma rays have more penetrating power in matter than charged particle. Gamma rays suffer attenuation of intensity and not degradation of energy. What does that mean? It means that gamma ray suffers attenuation of intensity. Attenuation means the number of photons. When the gamma rays enter in the detector medium or interact with matter, either they are completely absorbed or they are scattered. So, gamma rays suffer attenuation of intensity, means their number they are completely lost, means there is a loss of intensity, and not degradation of energy. It means gamma rays do not suffer the loss of energy in the medium. They are either completely absorbed or they are deflected, but they do not suffer the degradation of energy as we can see in case of charged particles. Charged particles when enter in matter, they continuously lose energy while interacting with the matter, but this is not the situation with gamma ray photons. Gamma rays interact with matter mainly via following three processes: photoelectric effect, Compton effect and pair production. So, now from this discussion it is clear that gamma rays, the behavior of gamma rays on interaction with matter is completely different than the way charged particle interact with matter. So as we can see that when the gamma rays interact with matter, they suffer the attenuation of intensity. And here we can see that in the picture given below, when the gamma ray of intensity I0 pass through a material medium of thickness x, then intensity I is observed on the other side of the matter, then I is equal to I naught exponential minus mu into x, where mu 0 is basically the linear attenuation coefficient, I0 the incident beam intensity, and x is the thickness of the absorber. Gamma rays, X-rays in matter. In this slide, basically we are going to study that how gamma rays or X-ray photons interact in matter. If the absorber thickness is measured in gram per centimeter square, then mu is called mass absorption coefficient. Mu m is equal to mu 0 upon rho. Mu is the attenuation coefficient and mu m is the mass attenuation coefficient. So mu does not change with the state of matter. This is very important, that attenuation coefficient does not change with the state of the matter, but mu m does. So it implies that if we are talking about mu only, then mu in case of water will be equal to mu in case of ice, and that is equal to mu in case of vapor. Mean free path, which is the distance between two successive interactions, can also be obtained if we know the value of mu. How? Because there is a relation between lambda and mean free path lambda and mu, that is lambda is equal to 1 by mu. So if we know mu, we reciprocate it, and then we can get the value of lambda. Half thickness is the thickness of given material to reduce the intensity of gamma rays to half of its value without material. That is d half is equal to log 2 upon mu, which is given in terms of centimeter or gram per centimeter square. So it means if we know mu, we can also find the half value thickness, and this is very important. This half value thickness for a given radiation is different for different materials. Gamma or X-ray in matter. So we continue our discussion, interaction of gamma rays in matter. Now in this slide, basically two pictures are shown. Picture on the left hand side shows the behavior of intensity of gamma rays as a function of thickness of the matter or thickness of the absorber. Now here we can see that when gamma rays pass through some matter, then their intensity continuously decreases. And here we can see that few marks which are represented as h half or 2h half, they show the point or the thickness corresponding to which the intensity observed after passing through the matter is half of what the gamma ray intensity was before entering the matter. So this is also called the half value thickness. On the right hand side picture, the transmission probability of gamma rays in lead for different energy gamma ray photons as a function of thickness is represented. Now here transmission means how many gamma photons will pass through a given thickness of lead sheet. So this is called a transmission. So transmission probability is basically, we can see that it decreases very fast as a function of thickness of lead, but it is a function of the energy of the gamma ray photon. Higher the energy of the gamma ray photon, more is the transmission probability for a given thickness of lead sheet. Gamma ray, X-ray in matter, photoelectric effect. Now as up to the previous slide, we have of the opinion that the gamma rays interact with matter via three different processes. Now in this slide, we are going to look into the photoelectric effect kind of interaction of gamma rays in matter. In this mode, that is in the photoelectric mode, the photon is completely absorbed by the bound electron of the medium, and photoelectron is preferentially emitted in the forward direction. What happens is, we know that in the matter, in the atom, the electrons are moving in closed circular orbits around the nucleus. So when the gamma ray basically hit and interact with the atom, then it interacts with the electron. Electron completely absorb the photons, and the photon is emitted. So that is called the photoelectron, the basic principle for photoelectric effect. Now the photoelectron is emitted with energy E is equal to h nu minus Eb, where Eb is the binding energy of the electron. Another important thing in the photoelectric effect we observe is that the probability of photoelectric emission is maximum for high Z materials and low gamma energies. That is, for low gamma energy means for gamma energies less than around 200 keV, we see that the photoelectric absorption is more, and the probability of photoelectric emission is proportional to Z to the power n upon E gamma to the power 3.5, where Z is the atomic number of the absorbing medium, that is material of the detector, and E gamma is the gamma energy of the incoming photon, where n is equal to n ranges from 4 to 5 depending upon the stopper. And here on the right hand side, one picture is shown. In this picture, the cross section of photoelectric emission is represented as a function of photon energy. Here you can see that the curve is falling down as a function of photon energy, with two kinks are observed on the lower energy photon side. One is called the L edge, another one is called K edge. K edge means when the incoming photon is absorbed by the K shell electron and it is emitted out. L edges correspond to the case when the incoming photon is basically absorbed by the L. So students, let us now summarize what we have learnt in this module. We have gone through many concepts in this module, but now it's time for us to recap what we have learned so far. The first thing that we have learned in this module is that electrons interact with matter in different ways than heavy charge particle. Second thing that we learned is for electrons too, the major energy loss in matter is via Coulombic interaction. Third important thing that we have learned is that for every heavy energy, for very high energy electrons, the energy loss via radiation increases with the atomic number of the interacting medium. The next important thing that we learned is that gamma rays suffer attenuation of intensity and not degradation of energy. From detection point of view, the half value thickness and mean free path of gamma rays in the medium are important quantity. Thank you.